Hello everyone, welcome to Design and Analysis of Algorithms. In this episode, we'll learn about 0-1 knapsack problem. In the last two episodes, we learned about fractional knapsack problem and unbounded knapsack problem. And in this part, we'll learn the OG knapsack 0-1 knapsack problem. In this problem, we are given n items a1, a2, an with associated integral size and profits. Each item ai, we are assuming it has size si and profit pi. And also we are given a knapsack of integral capacity B. And we are assuming all this data SI, PI, B, they are integer numbers. Our goal is to find a subset of items such that their total size is at most the knapsack capacity. So it should satisfy the knapsack capacity constraint. And we also need the total profit to be maximized. So unlike fractional knapsack problem, now we are not allowed to cut any item, or like unbounded knapsack problem, we are not allowed to use multiple copies. We can only use an item entirely, or we may not take it. So think of the example we talked about from Charlie and Chocolate Factory. Either you take the entire chocolate or you don't take it. So this is 0-1 knapsack problem. In the last episode, we talked about the unbounded knapsack and we wrote a DP. And I earlier mentioned that knapsack is already an NP-hard problem. So we don't expect a polynomial time algorithm, but we'll see there is something called pseudo polynomial time algorithm. We can still get a pseudo polynomial time algorithm for 0-1 knapsack using a dynamic program. So let's look at the elements of DP that we have talked before to design a dynamic program. So first we have to find some ordering, and then we have to go for the recursion. We have to find the optimal substructure property and show there is an independent and overlapping subproblems, which are the recursion takes care of all subproblems, but the number of subproblems are small. Then we have to build the table, and finally we have to show the runtime. So first about the ordering, we saw last time as well, there are two types of quantities. One is items, one is capacity. And subproblems we can consider either fewer items or smaller capacity. In unbounded knapsack, we took smaller capacity and that was fine. We don't need to take care of the items because always all the items were available because we can use multiple copies. But now it is more tricky. If we pick an item, because of 0-1 knapsack, we have to ensure that item is not chosen further for the remaining subproblem. So for that, we define this VIX to be the profit of the best solution such that it uses only first I items, 1 to I, and it has total size at most X. Under this, we'll see that if an item is I is used, then we'll go for the subproblem for I minus 1 and I will not be used further. So this is a recursion that if item, so we define VIX as it is. So VIX, if I don't take the item I, then it is the same as choosing the items from first I minus 1 items, because I item is not there, so it's just VI minus 1 X. On the other hand, if we choose the item, already we obtain a profit of PI from item I. But now, as we have placed the item AI, already item I or AI, already, so I'm using AI and I interchangeably here. Then we are left with I minus 1 items. We cannot use item I anymore. It's already used. And we are left with X minus Si space. The item has size Si. So we can only use remaining X minus Si amount of space. And there is one edge case. If already the size of the item is more than X, then we cannot use the item. So Vix equal to Vi minus 1 X. So in that case, this will become negative, X minus Si. To avoid that, if Si is more than X, we don't take the item. So Vix equal to Vi minus 1X. This is sufficient. We can create. So I'm not going over the proof that why this is the optimal substructure. We have already seen it's quite simple. You can just verify once more why this is the correct recursion. Now, iterative bottom-up algorithm we'll create. So we create an array, two-dimensional array. AIX. So in the previous example, we always had one-dimensional array for interval scheduling or Fibonacci number or unbounded knapsack, but now we have a two-dimensional array. And one dimension will denote the number of items I that we are selecting from 1 to I. And second one is capacity that we have right now, X. And this is containing VIX. And we initialize the array first. So we'll fill row by row. So first row, 0th row, is for when we don't take any item. So we just put that to be 0. That's the initialization. And total size of the array is n plus 1 times b plus 1, because there is a row for 0 size and a row for 0 elements. And then we run the loop, and the loop is just running the recursion. If si is more than x, this is the edge case we run. Otherwise, we run the usual recursion. And as we see, the number of subproblems are only small. Each step we're only considering 2 subproblems. So runtime is number of iterations we're doing is order NP, or number of table entries is also order NP, and per table entry we are spending at most constant time. So total order NP time. So just like unbounded knapsack, the runtime is order NP. But in unbounded knapsack, we had order n iteration, and each time we are spending order b iteration, and each time we are spending order n time because we're looking for each item. So it was taking order nb. Now we have more iterations, order nb iterations, but we are only choosing over constant number of subproblems. So it's still the same runtime. Now let's go over one example. And I'll highly encourage you to just pause the video and do it on your own, how this table is filled up. But I'll still do it partially, but you should do it at least once just to get a flavor how dynamic programming works. So in this example, we have 4 items, and we are assuming B to be 6, and P1, the first item has profit 3, S1 is size, first item has size 4, similarly second item has profit 2, size 3, and so on. Now we are filling the table. And as I mentioned, the initialization part here, we already filled the first row to be 0. This is completely 0 because we are just initially where we're not taking any items. Now let's fill up the entry for 1. So we are filling A1x. According to this, we are saying we are only using items, first I item. So in this case, I equal to 1. So we're only allowed to use the first item, or we don't use it. So a subset of either empty or the first item. And we want the total size should be less than or equal to x for the x entry. So now if I look at the item, it has size 4. So already this edge case says if the size is more than x, then the corresponding entry should come from the previous row. So if I look at here, size is 4. So for 0, 1, 2, 3, this is the portion where si is more than x. Si is 4, x is like 3 here, is still more. So for this 4, we cannot take the item. So we are just looking at the previous entry in ai minus 1x, which is a0x in this case. And we are getting just inheriting this 0 from here. But when you go to 4, then we have an option that we can either don't select the item and then we get 0 again. But if we select the item, then we have consumed 4 space. So we go to ai minus 1, x minus si. In this case, it will be 0, 0. So we go here and then we take the item and we get profit 3. So just verify this, pause it, understand why it is 3. And then we continue for the next item. Again, we have an option not to take the item, or we go to minus 4 and we get from value from 1. Or here also we get either item from here, we don't take it, or we get from 2, the same value 3. So this is second row is filled up. So note that though it's a huge table, actually we don't need to remember the entire table. We can just remember the previous row. I mean, for row 1, I just need row 0 to be filled up. So it can save some more memory if you want. In the next iteration, again, we are looking at item 2. So we can pack now a subset of items from 1 and 2. And 2 has size 3 and profit 2. So anyway, the first 3 elements will be 0 because si is 3 here and previous one was 4. So in both the cases, like the items are, if si is more than x, then we cannot pack the item. And then and in the previous case also we had 0, so it's just inheriting the previous values. And in this case, when we have x equal to 3, then we can either take the item, and in that case we get from 0 to 2 because P2 is 2, or we can get 0 from the previous entry, I minus 1, and base of this 2 is 2, so we get 2. And the next case, again, we get 0 and 2 here, or we do not take the item and we just take the item from the previous solution, which was already containing item A1, so we get 3. Same way we can continue even for this one. We either get the item 2, but then we get profit 2, or we get the item from the previous entry, which was item A1 already, and we get 3. So base of these two is 3. So this is the second row we fill up. In third row, we can continue like this. The third item has size 2. The first two entries become 0. And then the next entry is it's just getting 4 profit from here or here or here. And then, because I mean, we can either get 4 profit or we can get the profit from previous case, which was 3. The best of these two is anyway 4, and we continue. But when we come here, then we have an option to take the profit here 2 and then get profit 4 from P3, from A3. So 6. And here we can get profit from 3 and 4 from P3, so 7. So this is filled up, and the last row is filled up in a similar way. And when we go here, we get 4 here, and the last item has size 3 and profit 4. So I can take fifth entry and go to -3 is 2 here. It has profit 4. So 4, and I get 4 from fourth item, so 8. Similarly, here also I get 4 and 4, 8. We can also get profit from previous items, previous rows, but that is even smaller. So we get finally 8 to be the final entry. And that is saying that if I use items from first n items and I have total size 6b, then the maximum profit I can get is 8. So that is the optimal solution. So opt is equal to 8. And what are the items we are taking? If we look at the path from which we are leading to 8, then we see 8 is coming from this 4 by selecting the fourth item, and this 4 is coming from here by selecting the third item. So this is showing it's A3, A4, and total size is 2 plus 3 equal to 5, which is less than 6. So in fact, you can see even here we have an 8 entry, which is saying that even if I have size 7, size 5, I can still have the same profit. So increasing size by 1 did not give us more profit. So this is Knapsack's algorithm, and it's order NB time. Now let's look at the runtime more closely. In a problem like Knapsack or any other problem like minimum spanning tree or graph problems, we normally have two types of data. All problems may not contain both types, but there can be two types of data. One is objects like sets, graphs, they're objects. And other one is numbers. For example, in this case, cost or profit or weights in minimum spanning tree, and so on, size. So normally we use binary numbers to represent data. And let's say 6 is a number. In binary, it will become 110. But also we can write the numbers in unary. So the first objects, they are represented in binary always. I'm saying the second object, numbers, we can either represent by binary or we can represent by unary. So in this case, for example, 6 will become 111 So by unary means you explicitly write digit by digit. So if the number is, let's say, x, you have x number of ones following each other. Now, for NP-hard problems, we know there is, we don't know any polynomial time algorithm, but here polynomial time means if the input is represented in binary, we have no polynomial time algorithm. But surprisingly, some problems which are NP-hard, they can still admit polynomial time algorithm if the input numeric data is represented in unary, and then it is called pseudo polynomial time. And these problems are called weakly NP-hard. They're NP-hard, but they're easier because we can solve them in pseudo polynomial time. Think of knapsack. We have order NB time. So B, the knapsack capacity, in unary representation it will have length B, but binary it will have length order log B. If you think of order NB, it is polynomial in terms of unary data B, but it is still exponential. B is exponential in terms of order log B in the binary data. So as it is polynomial in terms of unary numeric data, it's a pseudo polynomial time algorithm. So just pause and understand what is pseudo polynomial time. And there are some problems for which they can be still NP-hard, even if you represent the data in unary fashion, and that is called strongly NP-hard problem. For example, bin packing is such a problem, and we might come across the problem later if we talk about approximation algorithm. So remember the definition of pseudo polynomial time algorithm, and weakly NP-hard problems. They're kind of easier problem to solve among NP-hard problems. Now we saw here there are two types of numeric data. One is size, another one is profit. And for size, we gave this algorithm. But let's in other case, if the profit is the data for input data for profits, they're small. Can we do better? Or can we have other types of dynamic program for Knapsack? So we'll see in the next part another dynamic program where It's based on the profits, not based on the size. So see you in the next part. Thank you.